course include some noise, which is impairing the communication, okay? And then in the end you have your 6 signal, which is S, that you get at the base station. Now, this is how any communication system works. You send some signal, the signal goes to a channel, you receive some signal, and then from the signal that you receive, you want to estimate something. That's, I mean, all this code is about this. You observe something, and you try to estimate something which is included in that observation, right? Now, this guy here, which is the noise of the communication channel, I would say that probably is like the most important thing, because like the reason why we all exist is noise. Like all telecommunication engineering, what they try to do, they try to find solutions in order to get rid of this noise.
What is BS and
Okay, this is base station, and this is user equipment. I mean, it's not important, it's just how I name it. Anyway, every doubt, if you have any question, just stop me asking, okay? Either in the sort of theoretical part or in the MATLAB code part, okay? So noise is very important, but that's just for the purposes of this first exercise. Let's just neglect it, okay? So now, in this case, what we know is that there is a mathematical operation which describes how this signal, which is the input signal, gets distorted from the communication channel. And this mathematical operation, you can probably guess which one is the convolution, okay? So this is the 6 signal X is just the convolution between the input signal U convolved, this is the convolution, sine H. Do you know what the convolution is? Okay. So can you tell me the definition of convolution? I gave you a hint. Please don't be shy. So what do you do if you have two signals? How do you convolve them? Sorry?
H, K, U, N minus P.
You say H,
K,
K,
multiply,
okay, U,
N minus P.
and minus K. Okay, this is correct. What you do, you take one signal, you flip it, and then you just shift the other one, and then you make multiplication, you sum them together. Now, the convolution is absolutely symmetrical, so just for the scope of this exercise, let's assume that we have the opposite, which is the same as your colleague said, which is written in this way, okay? So convolution, it's this operation where you have your vector, okay, which is the vector U, U0, U1, U2, up to, let's say, U and U, which is the length of this vector. And then you take the second one and you flip it, right? And then you have H0, H1, H2. Now, what you do is just take, element-wise multiplication, and you sum up them together. So in this case, the X0 is just this product here, right? Which is U0 by H0. Then what happens with X1? You take, you shift by one sample, right? And again, you do the same stuff again. So now we have this multiplication plus this multiplication. U1 by H0 plus H1 by U0. Is it okay? This should be pretty much clear, right? Now, there is one very nice thing, which is a very nice thing about convolution, which is the following one. It's a linear operator. Okay. So why is this so important? Well, because any linear operation can be represented in the matrix form. So if you have a linear operation, you are always able to, to write this as the product of matrices and vectors. So in this case, our This is basically how it works. And why do you think it's so nice that we can have something like this? Do you have any idea? Like, why it's so important to end up in a form which is just, the multiplication of several matrices? Because imagine you want to, as in any communication system, estimate this signal here. This linear system can be inverted in most of the cases. I mean, not always, but you know how to invert this, right? So you know that if you have x, and if for some reason, that will be, by the way, the focus of this lesson, you know also h, you know that you can easily estimate u. You know how to estimate u from this signal? Any suggestion? Exactly. So you have h, transpose h, minus, okay, sorry. I'd like to go here. By the way, my notation is like one line is a vector and double line is a matrix. Okay. Now, this equation here, let's say this expression here, is called pseudo-inverse. Okay? You may think about this some sort of matrix inversion, when the matrix is not square and under some specific cases. So this is sometimes denoted with this weird infinity symbol, right? Okay, this cross here. That's the pseudo-inverse. Now, so this is nice because in any engineering problem, what you do, you have a physical problem that involves physical quantities like channel, signal, and so on. The first step, you try to make a mathematical model to describe this physical model, right, which is this equation here. So you know that your signal is mathematically modeled by this equation. It's weird, but then the next step, you write in a form in such a way that you can easily manipulate it in order to get this, okay? This signal manipulation is signal processing. Any kind of manipulation, this signal is signal processing, okay? Now what I'm telling you is that this is a good way to estimate the signal u, right? Okay, that's pretty much it. This is the convolution, but now what is important is, do you know what's the shape of this matrix H? Okay, can I cancel this one here? Is it okay? So we have x0, x1, x, and x. And then we have like u0, u1, u, and u. So what goes here? Sorry? Okay. And then you, exactly, thank you. And then what happens to the second column of this? Remember, we have to shift. The second column is just a shift version of the first one, right? So this is the one, then you have another one here, and another one here, and so on. And then you see that if you make this multiplication, which is a row by column multiplication, you end up having exactly what is written here, right? Because you have h0, which is just h0, I mean, these are 0. You know, h0 by u0, which is this one here. Then in the second one, you shift, so you have h1, u0, h0 by u1, and so on. Okay, this is the convolutional matrix, and this is what we're going to implement right now. By the way, one last question for you. If u is a sequence with n u samples, I mean, this is something that you have to tell me, okay? And this one is a sequence with nh samples. So I'm convolving a sequence of nu samples with a sequence with nh samples. What's the length of the output sequence? Exactly. So it's as your colleague said, is nu plus nh minus 1. Okay? So, is everything clear? I mean, okay. So let's go on. By the way, I will write this code. So at the end of the lesson, we will upload this material online. So I mean, it's not. It's not mandatory that you write the code live while I'm writing it, because you will have the code later. What is really important is that you understand what I'm writing right now. If you have any question or problem, just ask me. Okay. Now, okay, let's start with this. I mean, when I start working with MATLAB, what I usually do, I create a script, okay, and then I save it like, let's call it convolution XM. Now, usually I start all my scripts with this, which basically means that you are completely cleaning all your MATLAB workspace, you're cleaning anything. Then MATLAB is going to complain and say this is not efficient, but for the purposes of this exercise here, I don't care. Okay? I mean, maybe there are some variables that are not needed to be completely cancelled. So now, with this symbol here, you open a new section, which allows you then later to run only that specific section if you want. Okay? And we call it convolution. So. Okay, now, let's start. Which parameters do I need? I need to know the length of the first sequence, which is nu, right? It's over there. Here. And let's set it to 10. And this is the input sequence length. I need to know the length of the channel, which is, by the way, just to let this more understandable for you, I'm adding these extra spaces between variables. It's not mandatory at all. Someone would say from a purely informative viewpoint that is bad actually, but just to let you understand, okay? Just to make it more clean. Okay, so now this is the channel sequence length, and then we have nx, which is the length of the output sequence, which is nh plus nu minus 1. Output sequence length. Okay, now, now we will generate two random sequences. Okay, so one sequence u and one sequence h, and I'm going to generate it as just a random sequence, where what this function is doing is just generating numbers randomly distributed between 0 and 1, okay? And anyway, if you have any doubt about how function works, what you can do, you can just take the command window, which is some tool you can use, and then with help, this is basically telling you whatever you need, and in this case, it's just written here. This is giving this vector which we are using now. Now, you put here the size of the number of rows of this matrix, and here the number of columns. This basically means that this is a vector of the desired length. Right? So this is the input sequence. Now we do exactly the same for the channel sequence. You don't need to write down whatever I write in the command window, okay? Just something to show you live some examples. And then, okay, if you want to clean the command window, you can use this CLC, which is down here. Okay, now let's plot some results. Okay, so I first open a new section. With this command, I open a new figure, and we will plot. Actually, for sequences, it's much better to use a function which is called stem. You will see how stem works in a second. And now we will plot our input sequence u. Okay, just to give a look to it. And then it's very important once, when you will require to write some kind of formal MATLAB code, just add units always. So this on the x-axis you have n, which is your index, and then on the y you have the un. Okay. So just give it to it quickly. Okay, this is what STEM does. Okay, it is showing you each single sample on the. Then on the x-axis you have the time index. Now, sometimes it may be useful to plot two different plots in the same window, so you can use the command subplot. Basically, in this case, the subplot is dividing all your figure window in 2x1 matrices. So by writing these, I'm making some kind of window where I can put two images in one column, and then I'm writing in the first of these blocks that I'm creating. And then, I don't know, we may be interested in plotting also channel, okay? So it's time H, and then just allow me to do this. We have the channel sequence. Once you run it, you see that you have these two figures in the same. By the way, this may be very basic for you, so if you feel like I'm doing stuff that you already know or anything like this, just let me know, and I will go faster or slower depending on what you prefer. Now we make the convolution, okay? There is a nice MATLAB function which is called conv, and basically what it does, it convolves two sequences. You can use it, and then as always, if you don't know what conv does, you just open a command window, you go on help, and then you see that convolution is convolved with these two sequences in it. Okay, now let's give a look to. So we open a new figure, and let's plot again this sequence. So x1, again on the x-axis you have n, here you have x1 of n, and this is the convolution by conv function, okay? Now, what we're going to do is now to make the convolution by conv matrix. And here is where I will need your help. So, we're going to build this matrix here, which is H, right? So, we are going to initialize this matrix. By the way, do you have any suggestion how to build this matrix? How do we do it? How do we build the matrix H? Any ideas? Yes, it is. Guys? One thing that we may do is to initialize the matrix H, scan column by column, and then in each column we plot our vector view in each column, but shift by one side, okay? So first of all, we initialize the matrix H, whose dimension is, where is it? Here. What is the dimension of matrix H? Is the, okay? Yeah?
Length of result of convolution is and the number of samples in your channel.
Okay, so it's nx by n u, right? Okay. Perfect. And now we build this matrix. We make a for loop that goes over the columns, right? And then we are going to plot into the matrix H the vector H. Here we want to know the index of the column, which in each for we're going to start column by column. So here is I, because of the first iteration, we're going to fill the first column and so on. And then here, we have to tell MATLAB which rows of each column, we are indexing, we are using. So this goes from, because at the first iteration, we start from this row, the second this one, so we again start from the row I, and then we end up in the row I plus exactly H minus 1. Okay? So, okay. Now we make the convolution, and let's call it x2, which is x by u, right? And then we are going to plot it and see if it matches the one that we did before. So stem x2. This is x2, sorry. And this is the right. Okay, let's check it one last time. The size is correct. It should work. So we run it, and then we see. And as expected, it's the same. Okay. Now, if you don't trust me in this, what you can do, you may plot the two sequences, one at the top of the other. So you take another figure. This is something that you usually do in these kind of exercises. You make the first one, and then you use the on command, meaning I'm not going to cancel what's already in the figure, I'm going to plot on the top of it. And then you have second sequence, which is x2. And then maybe, I don't know if this works like this, but you can change color, okay, in order to highlight the difference between the two. Okay. So if you look here, okay, I mean, sorry, the size is not changing if I'm zooming it, but it's okay, is it clear? Do you have any questions? Okay? Can I assume that you will perfectly know how to make a convolutional matrix? Okay? Okay. Now, why do we need this convolutional matrix? Well, let's come back 1 second for our example here, okay? But maybe I will need the whole black one now, so we'll start with. How does this work? Okay. Let's hope that then we will be able to switch it on again. It usually doesn't happen. Okay, now let's come back for our example, because as I said, you have a communication system, you send some signal U. By the way, now that we did this first exercise, we are ready to add back our best friend, which is the noise. So now this is a real communication system where the communication is impaired by this noise. Now you send some signal U, the base station receives some signal X, right? Then you are able to make this computation where there should be some noise here as well. And then you are able to estimate the data that the mobile phone is sending to you, right? Now there is something missing, okay? What is missing? I mean, the channel is missing. We don't know the channel, right? So even if you do this kind of communication, then the base station doesn't know what to do with this data because it doesn't have the channel. So do you know how this works in any communication system, how do you estimate the channel in general?
We send some training signal and then estimate the...
Exactly. So, training signal, what does it mean?
Professor said it to us.
No, I'm asking you, what do you mean by training signal?
Well, for example, we send an UT signal,
Okay.
and then we receive the XT
Okay.
result, and using that data, we can estimate using that formula.
Exactly. So basically what you meant is, UE and base station, they agree on the fact that the UE is sending some information which is known to the base station.
Yeah.
So I'm sending you some known information that what the base station does, giving this knowledge about the data that has been transmitted, estimates the channel, and then at some point, say to the UE, okay, now start sending me some real information, and using the channel that the base station has estimated, can do again this procedure, and finally estimating the data, allowing you to use it manually. Okay. So now what we are going to do today is to do what the base station does every day, which is estimating the channel. Okay. Now, I think we can reuse this model here, but now that you are confident with, say, this notation, let me say that the signal that you receive x, it is okay. Let me just cancel what we don't need. I think now we know what this is, so we don't need it anymore. This is just a reminder, but okay, just leave it here. No, I need this page, sorry. Okay, so now this kind of problem is similar to the one that we did before, but you got the signal x, which again is the convolution of the channel, h, the input sequence, which as you said we know, and n, right? Now, in the example I did before, we assumed that we knew h, okay? So since this operation is fully commutative, basically this is exactly like, So, when I said before, you have several steps in some engineering work. You have the physical problem, the mathematical model, and this is the mathematical model. It's the same as before, but we did it, right? And then what I said, there is a crucial step, which is, let's say, modifying your mathematical model in such a way that you can exploit, the information that you have available to reach your goal. Now, in this specific example, what we know is this, right? So what we do exactly what we did before, but we build the convolutional matrix, filling the columns of this matrix with the training sequence U, which is the one that we know, right? So now we are able to make something like this. Is it okay? It's similar to the other one. Before we had like H by U. Now we have this, similar but fully equivalent so far. But in this way, then we are putting ourselves in the position to be able to estimate this channel H, which is the final goal here. Okay, now once you did this, then is it okay? So what you do, you know that you can estimate H just taking our friend pseudo-inverse. I mean, there's someone that says that this is the most beautiful equation in statistics because it allows you to do anything. So once you reach this, you are done. Again, this is something you should be really aware of. I mean, once you have been able to write down this, your job as an engineer is almost done. Then it starts your job as a mathematician to invert this. But I mean, it's just a further step. Okay, now let's see why this is a good estimator. Let's just, if we plot this here, what we get is something like this. Okay? We just, this is the signal x, and then there's this pseudo inverse in the front of it. And now, what you may see is that this thing here is exactly this thing here, but with a -1 sign. So basically, they cancel each other, okay? And that's the beauty of what we're doing here, because in the end, you end up with your estimate, which is equivalent to exactly what you want to estimate, right? Which is h, because these two guys, they cancel each other, plus this term here. So this is nice, right? We want to estimate the channel, and the estimate of the channel is exactly the channel itself. And then we have the noise, which is, by the way, scaled down eventually by this matrix here. Okay, this is like an inverse matrix. So we don't only just estimate the channel, but we also scaling down the noise by this term here. So how do we know that this is a good estimator? When you estimate something, do you know which, this is a vector? How do you know that you are doing a good processing? I mean, imagine I give you this x vector, okay? I give it to you. Then you take it and you divide it by 10. Then I give it to you, you take it and you take the square root of it. And all of these are absolutely, they can be, let's say, referred to as estimators. You are doing signal processing, you are doing signal processing as well, you are estimating the channel. But is it a good estimator? Maybe it's not right. So, something that can tell you something about how good your estimator is called the mean square error, right? I don't know if you already did it, probably you don't, but have you ever heard about Kramer bound? Maybe you heard it, but you didn't compute it, right? Basically, the Kramer bound should be your best friend, because the Kramer bound is telling you what's the best you can do. You can't do better than the Kramer bound. It's the lowest, lowest variance that you can reach your estimation. Basically, if I make some estimate and the variance of my estimate is very, very, very low, it means that the estimation is very good, right? Okay. Now, the Kramer bound is telling you this is the best you can do, okay? So, now, Professor will be surely more specific on this point, like in the next lesson, but it turns out that for this specific example, if we make some specific assumption that in this case, like, this means that the noise is Gaussian distributed, okay, as well as the training sequence. It turns out that if you compute the covariance of this estimate, and then you add your data, which is the number of training samples that you have, go to infinite, then that's exactly the best you can do. That's the Kramer bound, okay? So, do you know how to compute the covariance of H? Because now we are going to compute the covariance of H, and then we are going to take like number of training samples, let them go to infinity, and in this case we will get this famous lower bound. Now, okay, let's do it last here. So, the covariance of H, what you do, you take okay, what is this? This is the error, right? This is the error between your estimate and the real channel. So basically, is this part here, okay? H estimated minus H error. Now, so okay, now we really need to ask you because so this is ut, right? Ut minus 1 ut n, and then we have this same thing transpose, okay? So when you transpose a sequence of matrices or vector, what you do, you take the last one, you put it in front of it, and you transpose it, and then you do the same with all the others. So basically, if we want to transpose this, you get NT, this is this one, which is transposed, then U, and then right? Now, this matrix is symmetric. Symmetric means that if you take it and you transpose it, you get exactly the matrix itself. Okay? So basically it means that this transposition is actually like having normal minus one, okay? Now, this expectation, I mean, what is the only random thing that we have in this equation? N, exactly. So basically, I mean, these are deterministic terms, right? So basically the expectation is just expecting this here. So, and we know this, right? Because we made an assumption over there, like it's Gaussian, normal distributed with variance sigma. So if you make, you know, a little bit of order here, what you get is this variance. Right? And then you have the second part. Is it okay so far? Now, you may notice that
N is a column vector or a row vector?
N
Is a column vector?
is a column vector.
Column vector.
When usually it's just you know, some default thing that people do, like it's a notation when you write you have a
So in
column.
this case, the expectation is an identity matrix, right?
Thank you very much. Okay.
No,
Thank you guys. Now, yeah, sure. This is a matrix, right? Because
Just to-
also because this is the covariant matrix of the vector. Okay, so we need to know all the elements in this matrix. Yeah, it is the identity matrix by sigma n, which is missing also here. Thank you again. Okay. Now, again, this is the same here, right? Minus 1 is go away. So in the end, what we get is this. And u minus 1. Okay? Now, we take this, we assume that we have an infinite number of training sequence. You know, if you have an infinite number of training sequence, it means that your station stays there forever, like taking signals that it knows, you know, that it already knows. So at the end, you end up with a very, very, very good channel estimate. But is it okay for communication? Right? No, because you're not transmitting any useful signal, right? But anyway, if we have an infinite number of training symbols, we reach, you know, ideally perfect performance. Now, if you take this, I mean, I'm not going to prove it, but if you take this and you assume that this matrix U is this, you know, where these vectors U are distributed as I put there, he found that let's just think about it as any, you know, a limit, like let's say the lower limit. This is equal to n over sigma u 1 over nu. Okay. Intuitively, basically you're just, you know, if you take a vector like this and then you sum up the vector, then what you get is that each entry of this vector has variance sigma u, but you're summing up nu of them, so you end up with this. Okay, it's something you can prove by yourself. But so this is the power of the noise. Okay, this is the power of the signal. So this is the inverse of the ratio between the power of the signal and the power of the noise, which is known as signal to noise ratio. So this is 1 over SNR, 1 over NU. Okay? Because U is the signal, the training signal is your, your a priori knowledge, let's say, and then you have the noise. So now, does this make sense to you? So we said that the good estimator is an estimator where in the end your covariance, your variance is very, very, very low. So this is telling us that if you have a very, very high signal to noise ratio, if the power of your noise is almost 0, you will get a great estimator. If you have infinite number of training symbols, you will get a great estimator as well. Okay? This is telling you that the performance of your system will increase, your estimator will be better and better and better as soon as you have higher SNR and a higher number of training symbols. Okay? And again, your colleague may I again forgot the mathematics. Okay, but this is a math.
In this question, covariance matrix and mean square error matrix are the same, I guess. But
I mean,
it should be a bias is 0.
Exactly. This is okay. What your colleague said is that mean square error and covariance, they are related by some relation, which involves also the bias. If the bias is 0, which means that the estimator is unbiased, then covariance matrix and mean square error, they cancel. Okay. Okay. Is everything clear? Now.
So we are not proving that equality, but
we're not doing?
We're not proving that equality.
That one over there?
Yeah.
No, I mean, not now. I think you can do it by yourself. Okay. But it's, yeah, of course, you can do that like.
I don't see how.
You don't see how. Look, the idea is that all this vector u, okay, but when you take the matrix, right, then you transpose, you have the u vector on the row. I just giving you some hint and not expect you to understand like straight away this. So basically what you're doing, you are multiplying several times this u vector, and so this is ut, and this is here, right? And each one, and this has n new element. And the variance of each element is sigma u, right? So if you do it several times, as many times as are the problems of that matrix, then what you see is that this product here on average is equal to n u times the variance of each element. N u times this here, which is over there, right?
Okay, I'll try.
Okay. That's it. Now, when I said if you have enough of this vector, I mean if you have enough training symbols, okay? Which is again written over there. Okay. Now, let me just okay, usually when you design a communication system, it's some kind of convention. What you do, you define your SNR as power of signal over power of noise. It's in some, it's not nice to have the SNR defined by two different parameters. So you can get rid of this just by normalizing the transmitter signal to 1. So basically, you assume that the signal you're transmitting in 1, and then you scale the noise accordingly, right? So you say that the SNR is 1 over the power of noise. All right? I mean, you will surely give a look to camera about the professor like more deeply, but this is just a flavor of how it works and what it means, right? Now, let me use this part of the blackboard to set up our simulation environment, and then we'll implement it.
Can I ask a question?
Sure.
In the Robertson matrix, you transpose Q. Every row multiplied by every column are orthogonal apart from the because it is distributed as
apart from itself.
Exactly. So second row by first column is 0, right?
Yeah, on average, yes. So that's why it's diagonal in here, right? So let me cancel this back here. Okay, I will just write it again. Okay, now we are going to implement this. Okay. Now we have one parameter. What we're going to do, we're going to list all the parameters that we need in order to set up the simulation. I mean, my goal here is to show you that the action of implementing itself is not that much important. If you know what to do, it's just straight away. Everything is done by planning, thinking about how you structure a problem, and once you have your problem structure well defined, writing down is just using MATLAB as any other calculator, okay? I mean, and that's what I'm going to show. So, okay, these are the same. Then we have the length is nx here. Then, now let me just drop the dependence on time, because we are going to deal with vectors. What else do we need? We need to know that the SNR is 1 over the power of the noise. We need to know that sigma u is equal to 1. We need to know that our limit is equal to 1 over SNR and u. Now, what else do we need? Well, we need to know the channel. Okay, how, I mean, we don't need to know the channel, but we have to, you know, once we simulate it, we need to decide what the channel is. And so we make our channel in such a way that each element of this channel is 1 minus A over NH for that goes 0 to NH minus 1, and then 0 elsewhere. Do we need something else to set up the simulation? We have the SNR, we have the parameter bound, we have the channel. I think we are pretty much, I mean, just to make it easier, just let me write down the model which we will use, which is x equal to u plus n. This is nx plus 1. This is nx nh. This is nh1. And this is nx1. So when I will be writing all the vectors, you will tell me easily what are the sides of the vectors and so on. And that's it. Now, the approach that we will use to make the simulation is called like Monte Carlo simulation. It's a kind of fancy name to say that you are doing some task several times, then you take the average. So basically, what we will do, we will first generate the signal. When I say signal, I mean the received signal x, okay? And the received signal x usually always depends on some randomness, some uncertainty, which is embodied in this vector here, which is the noise. Once you generate the signal, you estimate the signal. I mean, not the signal, you estimate what you are interested on, which is the channel. After this, you compute some metric, which in this case is going to be the mean square error, the mean square error. And then, you do it again several times, okay, with different realization of that random vector there, and then you average the results and compare. Okay? Okay, here we are. Let's make a new script and we call it channel estimation. Then as always, sure that we clean all the previous example. We open a new section, we call it channel estimation. Okay, now we have everything there. So let's start, defining our parameters. So first of all, we have NU, which is the length of the training sequence, right? It's the number of symbols that we will use in order to estimate the channel. It's the data we have. The more, the better. Okay? At least if the goal is estimating the channel. Let's start with 15 and we will see. So this is the length of training sequence. Now, the channel. Generally, it's good to have a number of training symbols which is fairly higher than the number of channel depth that you want to estimate. The number of the length of the channel. Okay. So this is the channel length. Okay, now NX, which is the results of this convolution, is NU plus NH minus 1. And this is the length of received sequence. Okay, what else do we need in order to set up our simulation? Look, my goal. Sorry?
Random variable.
Yeah, but that's going to be like after we define all the parameters, we will start a loop over several iterations. That's where we will put the vectors. Exactly, because the goal is to test this estimation algorithm for different values of the SNR. So yes, we will need a loop in order to make this several times, but we are going to do this for each SNR value. So we define the SNR. Usually you first define the SNR in dB, okay? And by writing this, I mean that we are going to test all the values between -10 and 20, okay? This column here is refers to this the range operator from -10 to 20, okay? I mean, if you run it, it is like just listing all the values. Okay, so now try to guess, like, after defining the SNR in dB, what's the immediate next step that you always have to do?
Linear.
Great. How do I do it?
Divide by 10 and
Exactly. So that's what we do. So we take the SNR, we divide by 10, and then we take the power of 10. Now, this symbol here, I put it because if I don't put the dot, what happens is that MATLAB is complaining because we are dealing with vectors, okay? So MATLAB is telling me, hey, put the dot because this is a length. Okay, so I follow MATLAB advice and they put the dot there. Now, what else do we need? We need to know how many times we are going to run the simulation for each SNR values, and this is called the number of, we can call it like Monte Carlo iterations or just iteration. And then the channel. Okay, we need to define a channel which is there. So first of all, I need to define the support for the channel, right? And this is a vector that goes from 0 to nh minus 1. If you define a vector like this, you will get a row vector, okay? Actually, it's usually better to have a column vector, so what we do, we take the transposition of this. And then you see that this vector is just column vector. And then we compute the channel by 1 minus all our indices over nh. So this is the channel support And this is the chunk. What else do we need? Any other parameter? Camera bound. Okay. So the camera bound again is 1 over the SNR over NU. Now I'm putting this here because again SNR is a vector, and if I don't, MATLAB is going to do some weird thing. So this is the Kramer bound. What else? I think it's. Okay. Well, once we have defined the SNR, what we need is the power of the noise, okay? And we get the power of the noise by just taking the inverse of the SNR. Let's call it, is it there? Let's just call it PM, which is power of the noise. And it is 1 over the SNR. Now, it looks like we have everything. We are going to run this for each SNR value. So we're going to initialize a vector called mean square error, which is going to collect all our samples. So to do this, we use the function zeros, which is creating this array full of 0, and the size of this array, it should match the size of the SNR vector. Okay, so we initialize the mean square error vector. Okay, now we are ready to start our loop. So we make an outer loop over the SNR values, and we do this by the function for. And we should run this as many times as the number of elements of the vector SNR. And I mean, this is just what I usually do. If I'm making a loop over some variable, what I do is to define the index, which is defining that loop, which is somehow similar to the variable under consideration. In this case, it's I SNR, which is the index, which is addressing that specific value of the SNR vector. Right? Okay. Now, once we have the SNR, what we have to do is to first define our input sequence, okay, which is the sequence U. Now, it's just, it's just some convention. I'm not doing it for some specific reason, but I'm just going to define the U sequence inside this loop, and we said that this is normal, okay, distributed with variance 1. And this is the function which is doing it, and this is our input sequence. Also consider that even if this is a random variable, actually the only variable we are averaging the results over is the noise, okay, in the other loop. So that's why we're putting it out of the main loop of the simulation. So once we have the input sequence, we have to go to the first point of this loop, which is generating the received signal. So AK goes to 1 to K. We are going to do this K times, and then we have the received signal. Okay, now tell me, how do I write the received signal? Which is X. No one?
You have to generate the random noise and multiply the input with the matrix, non-matrix, and
Okay.
the
Random noise, then I make the convolution, and I can either generate some convolution matrix, or I can just use the function count, right? But actually, in general, this is just some abstraction that we are doing just because we are simulating it. But in general, you get the signal, you don't know how it's generated, and then you use the convolution matrix just to make the estimation. So basically, we get the signal, which is the convolution between H and the input signal U. We add some noise N, which I haven't defined yet. So we define the noise. Now, so we know that the noise is again a random vector, Gaussian distributed with n, how many elements? Yes? X?
And in this case, we are generating noise every time, every cycle,
Yes.
every yk, and not for every ysnr.
I mean, it's inside the loop, so you're doing it for each SNR in each iteration. But then what it changes is what we say right now, which is the power of the noise. Okay. So how do we? I mean, this is to generate just a vector, which is with zero mean and unit variance. So how do we make a vector with zero mean but sigma, say Pn variance? How do we do it?
Multiply by sigma.
Okay. So like this, you mean? This is sigma squared, right? Is the value. So to get sigma, you take the square root of it. So basically you multiply by the standard deviation, which is the square root of the power of variance that we have in our vector Pn, okay? And this is done for the value at this iteration I SNR. Is it clear? No. For each one of these loops, we just make the power of the noise changing over and over, okay? So now we are in the first SNR value, we are generating this random noise, and the power of this random noise is exactly 1 over the SNR. Okay, so we have the received signal. Next step, estimate the signal. Okay, channel estimation. So, how do we estimate the channel? We make the convolutional matrix, right? Now you are expert on doing it because we did it like 5 minutes ago. So we have the matrix is now U, right? So we build our convolutional matrix, filling it with the training symbol U. So U, we initialize it, and the size is N, X, and H. As we did before, now you make the fourth cycle, 1 to an H, and we are going to fill up column by column this matrix U. Is this okay? What I'm doing? I mean, I'm putting the H here. I just realized it, but guys, help me out in this. This should be U, right? Okay, so IH to IH plus NU minus 1, right? And so basically, as you were saying before, you know that this actually is exactly like, U by H plus N. So then this is very useful because we can just get H estimate by inverting this stuff here.
There is some built-in function for this.
Sorry?
It's easy, but there is some built-in function for convolution matrix.
Are you asking me or are you saying it?
I'm saying.
Ah, okay. Okay.
Conv NTX.
Okay, let's see it.
Let's check.
Conv
NTX.
I'm useless if this function exists. Okay, anyway, I mean now we know how to do it and now you know how it works. It's always good to know this new thing, but yeah, in general, if you want to show someone that you know how to do things, it's better to try to not to use too much built-in matter functions. Actually, there's another way to do it, but we will see it later. Now, thank you. Okay, so now we estimate the channel. And how do we do it? Pseudo-inverse. So we first invert this matrix here. And then this is the pseudo-inverse, okay? Basically, this is the matrix product between the transposition of U, which I cancel, I'm sorry, and U, and then this is multiplied by U transpose. And then you multiply this by the receive signal. So this is the proper channel estimation step. Now, how do we define the error? Well, the error is H estimated minus H. This is a vector error, right? Because we get an error for each element of the channel. Okay. So next step is the computation of the mean square error. So how do we compute the mean square error? I mean, we take the error, we square, and we take the mean. So basically, you have your error, you square your error, and then you take the mean. But just for the sake of to be as clear as possible, just let me compute the error, the mean, like manually, even if there is a function which is called mean. And the number of elements is nh, okay? Because the error is telling us error for each element of vector, error vector. And now this is for this iteration, which is the iteration ik. Now what we're going to do, we also have to average over all the k iterations. So we sum up all these errors, and we do it like this, directly storing this value in the MSC in the position corresponding to that SNR value. Okay. So now we are summing up all the errors. This is the error for the iteration ik. Okay. What we have to do at some point is to divide this by the number of iterations, which is k. And we can do it like directly inside here. Okay. So basically, instead of summing up all the errors and then dividing them by k, what we do, we sum up this small error contribution, which has been weighted 1 over k. It's called running mean, but in the end is exactly the same. And then I think it's okay. We are pretty much done. So we end the first cycle, we end the second cycle, and MATLAB is complaining. Let's see what MATLAB has to say. Okay, yes, I mean, MATLAB is saying, sometimes MATLAB gives you some suggestion, and most of the time they're about complexity, like how you can do stuff in a more efficient way. And now I'm saying that instead of writing this thing, it's apparently better to, I mean, it is better actually, but it's to use this symbol here, right? This is more efficient. But I think it's just for us for now just more immediate to see it like this, just at the this step. But we can write it just like this, just to know that this possibility exists. Okay. Okay, now we plot the results. Figure 1, and then it's the MSC is going to be some very small value. So in this situation, it's better to plot in log scale, the y-axis. Okay, so plotting the error in dB scale. So there is a function for this, which is called semi-log y. It's basically taking the input, and then it's just okay, this is stupid. Sorry. So we take the SNR in dB here. Oh, the camera bound. I forgot about the camera bound. Okay, let's define the camera bound first. I defined the camera bound. So first we plot the camera bound. Then we want to compare it with our estimation, which is given by the mean square error, and then just to make it a little bit more clear from just to display it there, let's make red circle. Okay, now on the X label we have the SNR, which I put it in dB scale. Then you have Y, axis. And here we have the MSE, mean square error. Let's put also some title, which is channel estimation. Okay, since we have two things on the same plot, we put a legend. So in this first argument here, we write that this is basically theoretical bound, which is given by the Kramer-Rao bound. By the way, sometimes it is also known as Kramer-Rao lower bound. And then we have the simulation. Okay. By the way, MATLAB is a tool which has been designed for mathematicians. Okay, it's not much of for like from an informatics perspective. It's more like about mathematics, computation, this kind of thing. So MATLAB is highly optimized for making operations that involves like matrix and vectors. Okay. So I'm saying this because I mean you would probably never find something like this in some kind of efficient code. Do you have, because this is a vector. Okay, this is a column vector. What we are doing, we are squaring, we are like elevating to the power of 2 every single element of the vector, and then you are summing up all the vector, right? And then we are dividing them by NH. Do you have in mind any other possibility to compute this? Like, exploiting these matrix to matrix or int vector to vector multiplication? Sorry? Okay. Okay. Exactly. Yes. So what your colleague is saying is that you could compute this just by doing this. Is what you're saying, right? Yeah, exactly. It's correct. And the reason why it's exactly the same is that vector is a column vector. Before we were, taking these, we were doing what we have to do is this, right? So summing up all the elements square. So what she's saying is that these can be computed just by this, which means that we take this. Do you all agree that doing this is exactly the same as doing this? Okay? I mean, this is nice. This is also a little bit fancy, but more importantly, it's efficient. Okay? So this is something which is which you will find commonly in like MATLAB code. Okay, now I'm trying to postpone in this moment as much as I can, but now it's the time to see if this works. And usually it doesn't, but I'm pretty sure you have been, paying attention so you can see. Wait. Okay. It works. I mean, yeah, it works. There's some slight discrepancy between the theoretical value and the estimated one. Then we will try to see why.
Maybe because you used twice the mean square error. I don't know if you used two times. Maybe.
Yeah, maybe it's good.
You sum up a lot of terms and it.
Thank you. I forgot to to comment this. Okay, I mean both are correct, but it's better to use just one of them and not both of them at the same time.
If you want it to be faster, maybe you should put when you construct the U matrix, you should put that outside the inner form.
Oh, that's another nice idea. You mean here, right?
Yeah,
so we take this.
And you put it outside the inner form.
Yeah, because that just depends on this.
Yes.
Thank you. Exactly. Now in MATLAB, when you make like Control or Command I, you just align everything. So now let's see if now it's faster and more precise. Good. Okay, so the blue line is the theoretical bound. Okay. Now, as we said, these the theoretical bound and the MSE of my estimation, they are exactly the same value under the assumption that the number of training symbols goes to infinity. Okay. Now we are using 50 training symbol. Is not really infinity. So what we expect is that if we increase this number, we will see all these red dots to be completely aligned with the Kramer bound, right? So let's try to do it. But there is the risk that it's going to take a lot of time. Okay, maybe what we can do, it's a trick which I usually use because I'm not very passionate, so I want to see what's the progress of the code. We can make probably this printf, and we can at MATLAB display as on the the command window in which iteration we are. So basically, iteration for SNR equal to the db completed congratulations, and this is SNR db SNR. Okay, so we started. Okay, sorry. What you have to do, you also have to tell MATLAB, to do this. Otherwise, it's going to display everything like just one beside the other, one, after the other, and then. Okay, right. Now, how many training symbols we have? 1,000. I don't know if it's enough. We can increase it a little bit more now to see. Well, it's better, right? But I'm not satisfied. I want to push it further. So let's make it more. Okay, now we will stay here until 6 to wait that my conclusion. Okay, do you have any idea how to speed up this a little bit? Do we really need to check any SNR value? What we can do is just to test the code in less SNR value. So what you can do, you can just stop your code. And then just checking the SNR, not for all the values, but just from, step 5. And this is surely going to be faster. It's not faster, it's just you check the estimation less SNR value. Now what we expect is to see our estimation which perfectly matches the Kramer bound, okay? So what happens if I use 10 training symbols? What do you expect to see in this plot? Imagine, I reduce NU 10 samples. How does this change? Exactly. Let's check it just for being sure. Okay, just plot. Okay. This is telling you that the more data you have, the better is the estimate. Okay. And then also the effect, you can see also the effect of the SNR because you see how the Kramer bound decreases by increasing the SNR. Right? Okay, so now another thing that you can do sometimes if the result that you're getting does not expect what your intuition is sometimes try to run this for more iteration. Okay, so increase the number of times you are averaging your results. But I think that for this sample, 1,000 k equal to 1,000 is probably more than enough. And then, of course, if you try to reduce this, then in the end you end up with something which is not correct. And the same, of course, happens if you increase the number of samples of the channel. If I have 100 samples, this is telling you that you're using 10 samples to estimate 100 samples, right? So again, if you run this, okay, sorry. It will take a lot of time, so again we used the trick we did before. And then what we expect is again something which is basically just a bad estimate of our channel. So this is how today's communication system has estimated the channel. You know how to do it. It's, you see, I mean, it's easy, it's basic, it's not that much complicated, but it's actually a good example and of what you can do with MATLAB and all the the kind of situation that you can simulate. Do you have any questions about the code or how I did it or the results? Is everything clear?
I don't understand only one thing, but I just don't remember why the support of the H is defined as 1 minus what?
You mean the support here?
Yes, exactly.
Why is
1
it?
minus the support divided by H.
Ah, okay. Here, I mean, it's not always like that. It's just the model that we chose at the beginning. Sorry.
Okay.
It's just the model we chose.
Okay.
Okay. Yeah. So basically, we said, okay, let us assume that the channel is like this. Now, give a look to the how. If you see, if you look at HM, no H. Okay. Thank you. You see that it's reasonable. First of all, because the maximum amplitude is 1, and you know, if I send some signal, it's very weird that after meters and meters, the signal arrives with the power which is higher than the power of the signal that I transmitted. So it's good that, I mean, the maximum, amplitude of the channel is 1. It means that the signal, of course, cannot, increase the power during the path from the transmitter to the receiver. And then you see that this is like has this decreasing trend. Now, another thing which can be interesting is just sometimes if you want to verify that some matrix or vector has some specific structure, you can just plot the element, and you can do it with the function images. So in this case, it may be interesting to see the the structure of matrix U, and you see that. Okay, let me do it for less. This is not very clear. Amazing. You see, this is exactly what I've been drawing at the blackboard for the last 2 hours. Like each column, shift by 1 cent. Okay, this is exactly what we were expecting from a convolutional matrix. And by the way, do you know what's the name of this specific algebraic structure of this matrix? If you sit on this corner there and you look at the diagonal, all the elements that you see are the same. Exactly. So potentially we can implement the matrix by using the function tuplets, right? Which I think is tuplets. Okay, so basically tuplets is telling us that we have to give an input, the first column and the first row. Okay, let's try to do it, since we have 4 minutes left. So we make U1, which is a tuplets. Now, what is the first column? It should be the first element of the channel, right? And then a vector of zeros. How many zeros? Okay, minus 1, right? No, this is the first row. Or the column, sorry. It's the column. It's the column, so I'm wrong. So this should be like just H, and then as you were saying correctly, we have nx rows minus nh, right? And then I lost it a bit myself. Is it correct? Yes. And then we have the first row, which is the first element of H, and then we have nh minus 1, right? Now we don't want all the code to run again and again, so we make this breakpoint here. It means that the code is going to stop there. We run it.
I think we should have a semicolon there.
Where?
H, not comma, but semicolon.
You mean here? For sure. Okay, when you have to concatenate different vectors, If you want to concatenate like column-wise, you have to put like semicolon. So let's see if now it works. Let's make some first example. It's brown. Okay, why is brown? I mean, the size is correct. Oh, because of course it's made by the matrix U. It's not made out of the matrix H. Okay, so minus mu. Right? Okay, now it should work. Perfect. Any suggestions? Why is it working? Okay, so U, first column, first row. I have no idea.
You
guys.
should also have a semicolon in the
I know, the reason why is that I'm stopping the code before computing the matrix there. So, okay. Okay, now I'm pretty sure it's going to work and you can go home. Okay, that's it. So thank you for the suggestion that this method works. Okay, that's it. So if you have any questions, this is the right time to ask them. Otherwise, see you next time.
You will apply to the right?
Yeah, sure.